Welcome,
Okay.
you 25.
Okay, thank you. And I also want to thank the organizers for the possibility to give a talk at this nice conference. In my talk, I will consider very simple and maybe most simple model of the open quantum system, but it is widely used as a test model for different approach to open quantum systems. So this is why I hope that the results obtained for this very specific, very simple model could be generalized in the future work to the other models as well. So this is the outline of my talk. I will start with my problem and with the definition of my problem and formulate the main results. And only after that, depending on if I have or not would have a time for it, I go into details and some discussion not only density matrix evolution, but also evolution and correlation functions and some counterexamples. And then anyway, I will go to the conclusions. Well, I consider the two-level system interacting with the heat bath two-level system have the Hilbert space C2. The heat bath is nothing else but bosonic heat bath. So it could Hilbert space is a bosonic Fock space with usual creation and annihilation operators. I will denote it as BK and BK dagger. I will denote the vacuum state in this space as a back. And I also have sigma plus usual definitions for sigma plus and sigma minus operators acting in C2. I consider the following model. It is nothing else but the spin boson model in the rotating wave approximation. Rotating wave approximation means that I have no terms of the form sigma plus B dagger here, only the terms which preserve the number of particles. So it is actually possible most disadvantage of this model, but exactly this approximation makes it exactly possible, at least at zero temperature. For zero temperature now means that I have very specific initial condition, namely I have some density matrix in the which acts in the C2, and I have very specific vacuum state in the Fock space, and I consider so the evolution of my both system and heat bath is governed by the Liouville-von Neumann equation, and then I consider the reduced density matrix of the system, tracing out the reservoir degrees of freedom, and I'm also go into the interaction picture. It could, if for this case, it is possible to do it in already after tracing out the heat bath, but of course, usually one have to initially move to the interaction picture and then trace out the heat baths. But for this special model, it is the same. It is due to our free evolution commutes with interaction term and commutes the free evolution of the vacuum state is constant. It's preserved the vacuum state. And very, I think, most rigorous and approach to the derivation of the Markovian master equations are based on the called Bogolubov-van Hove scaling. Namely, one should consider, we have usually some small coupling constants here, but to derive the Markovian master equation, one should not only go to the zero limit for the coupling constant, but go to the long time limit for the times. And more specifically, one should introduce the following matrix, which is this reduced density matrix in the interaction picture with timer scaled with this -2 power of lambda, the same small parameter as is in this coupling. Well, and from the physical point of view, this scaling allows one to separate the time scale on which the Markovian behavior occurs from the time scale of order of reservoir correlation time. So it's just general idea of Bogolubov about time scales separation, and not only, and then Van Hove and many other people after them. Well, but it's many literature about both about reduced dynamics of the Bogolubov-van Hove limit, and as well about the stochastic dynamics of both system and heat bath in this coupling limit, which could be found here. But I will speak about all the perturbation theory in this lambda, not only about the real zero term of the occurring when lambda turns to zero, but about all the asymptotic series in lambda. And there are not, as I know, there are not much information known about these corrections. I think there are these 3 papers which discuss it in stochastic limits style, and there are some papers, for example, of Van Kampen, when not directly this story is described, but it is possible to, if it is on very physical level of rigorous, but the similar situation are described there. But still, I haven't found in literature very wide discussion of the all orders of the perturbation theory in lambda for the Bogolubov-van Hove scaling. And I will obtain so-called Gorenicki-Sokovsky-Sudarshan-Libland form equations with constant coefficients. So for those who do not know it, then this is just the definition of the Gorenicki-Sokovsky-Sudarshan-Libland form. Here is H is self-adjoint. For me, rho, it would be just finite dimensional matrix. So H is self-adjoint and C are arbitrary operators. It is just a most general form of the generator of the completely positive evolution. Okay, my main result is the following one. Let this integral from the physical point of view, it is the reservoir correlation function, nothing else. Well, in the interaction picture, then let this integral converge and define continuous function g of t with finite moments up to m+1s for some natural number m. Then there exist such constants such that the solution of this equation of this Korinka-Tsiolkovsky-Sudashan type equation approximates the exact evolution. Rho t and lambda is exact evolution defined here. Approximates the exact evolution with the asymptotic precision of order lambda to the power 2m+2. If we turn lambda to 0, it is very important for fixed t. It is meaning it is not homogeneous asymptotic precision, not homogeneous in time. It is not valid for the times of order of lambda squared, for small times. It is valid for fixed t strictly greater than 0. This is important for further discussion. And so this is the main result. And if we have infinite number of finite moments, so our correlation function is well localized in time, then one could obtain the description of the evolution in terms of GKSL equation with constant coefficients up to arbitrary perturbative order. This is important that one may think, oh, it means that it is exact. It is not exact because it is possible to have a contributions which turns to 0 faster than every power of lambda. And actually, it is very important. Usually, this is the case. To obtain this GKSL type equation, one should forget about these corrections, which I usually call non-perturbative, which turns to 0 faster than every power. So this is the main result, and here are some details. Namely, for me, maybe the most important detail is that the initial condition. So the initial condition for my asymptotic approximate equation is not the same as the actual initial condition. So this sigmas is exact initial condition, but the initial condition with for these equations should be changed to some other initial condition. It is the usual situation in the singular perturbation theory. It's called boundary layer phenomenon. So it's nothing else that the initial condition for exact result and for the asymptotic one do not coincide. And what is important, first of all, it is important that they not coincide of order of lambda squared. So because somebody may think, oh, maybe I have some asymptotic solution. Maybe it is possible to fix them by some asymptotic manipulations of order of lambda to the power 2m+2. But no, it is the difference between exact and asymptotic initial condition is sufficient. So this valid for t greater than 0, but this precision is totally invalid for t equals 0. And what is also important that if real part of the first moment of the correlation function is greater than 0, then this initial condition is even not a density matrix for some sigmas. So for some real density matrices as initial condition for the exact evolution, they are even not a density matrices. But of course, after some time of order of lambda squared, they became a density matrices for arbitrary initial conditions. So the main idea is the following. So one could describe such a sort of Markovian actual evolution by Markovian equations, but with non-physical initial conditions. It is possible. It is one way to think about it, at least one way. And it was mostly unusual for me that okay, you have very usual, very good completely positive evolution, but it is important that you have to obtain the true asymptotic precision. One should make a bad initial condition for it. So I think it's most tricky part of the story, and it is better to show it on the examples. This model is, as I said, in social sense, it's exactly solvable, and at least it's exactly solvable for the exponential correlation functions, because it's related to some integral differential equations which can be solved exactly in terms of the situation of exponential kernels. And the situation is the following: that we have exact evolution, which is blue. We have my evolution here. It's possible to calculate it in all orders of the perturbation theory. It is orange here, and it is obviously see that it is not valid. Gamma here is a parameter which is correlation, which is reverse correlation time. So we have time in the units of the correlation time. So my approximation is not good at the small times. It's from the asymptotic theory. It's times of order of lambda squared. We have this non-physical layer, initial layer of my evolution. Here, for initial condition, I should use not a density matrices, but a matrix with population greater than 0. Of course, the probability is impossible to be greater than 0, so it's totally unphysical. But if one instead would use the physical initial condition, then it would be very bad coincidence between exact evolution and the evolution followed from the my JKSL equation. So it is totally important to make non-physical initial conditions here to obtain the true asymptotic behavior. And here mostly similar situation, but here the perturbative blue is the same, it's exact. Green here is just usual weak coupling limit, Garini-Kosakowski-Sudashan-Liblet equation, so it's usual result of weak coupling limit, and orange line is my equation just in second order of perturbation theory, so not just this first correction. And I'm just showing that it is this correction is actually important, because maybe some could think, oh, I could use just weak coupling limit equations and it is maybe enough for me. But there are some contributions from this perturbation theory, and of course. I said that it is not valid at the initial times, but at the initial times there are possible to make other small time expansions and then match the results, and then it is possible to obtain uniformly good approximation. Uniformly, I mean uniformly in time. and this red one, this red line is uniform approximation. But of course, for initial time, it is impossible to use GKSL type equation without at least time independent. Here's another possibility. I said that there are there are situations when I give a certain condition here that if real part is greater than 0, then it is even not a density matrix. But even in the situation when it is a density matrix, as in this case, it is also one should change the initial condition to some other initial condition. For example, here the initial condition for the density matrix, for the actual exact density matrix is 1, and for my equations are less than 1. And in this situation, we have also the same story. We have bad approximation of the initial in this initial layer. For example, exact evolution is some oscillators, and but we have good approximation after 1 or 2 correlation times. So in practice, just after 1 or 2 correlation times, these equations, these just JKSL equation with constant coefficients give good approximation. But also one should use another initial conditions than usual. So it is important, for example, in weak coupling limit, for usual weak coupling limit, we have this green line, and it is possible to see that orange line is closer to the blue line. So these contributions are important. But actually, in this situation, is even maybe not so important. But nevertheless, it's possible to make better precision with these perturbative JKSL equations. And here I have considered a bit more complex situation when I have several sum of exponentials in the kernel. So it's a bit more complex initial behavior. But after 1 or 2 correlation times, it becomes just very simple behavior governed by the usual Markovian GKSL equations. So it is possible to bind all the non-Markovianity or non-stationarity at the very small time periods, and after these time periods, everything becomes Markovian. And of course, it is also there are different approach to the Markovianity, because there are a lot of results. Many people now think about Markovianity as JKSL equations only, but even in the classical case, Markovianity tells us not only about one-time evolution, but about multi-time evolution. For example, about correlation to time correlation functions. And there are actually different possibilities for the correlation functions with the same JKSL evolution. And in very old papers of Feller, it was shown that it is possible to obtain usual Markovian master equations, but totally non-Markovian dynamics in terms of multi-time evolution. So even in classical case, so it is for quantum is of course also interesting to understand if it is classical or not, if it is Markovian or not in terms of correlation functions. And in terms of correlation functions, the Markovianity means that these correlation functions could be calculated by a so-called regression formula. So I denote the correlation functions calculated by the correlation formula by this thing is M. So this is Markovian correlation functions. But here it is possible to calculate exact correlation functions, just considering unitary evolution in both system and heat bath. So it's possible to calculate exact correlation function. And Markovianity in terms of correlation functions means that this calculation should be equals. There are some old discussion of it starting from Liebland, then by Accardi, Frigerio, and Lewis, and some novel discussion of different types of Markovianity in this PhysRep review. But strictly speaking, outside the usual weak coupling limit, outside the zero order of perturbation theory, it is dynamics here is non-Markovian in terms of correlation function. Namely, but in zero order, it was showed by Dumke that correlation functions could be in weak coupling limit could be calculated by generalized regression formula. But outside the zero order, it's not Markovian, but and it was pointed, for example, here, but it's non-Markovian only up to a constant. So all the non-Markovianity also arise only in this slippage of initial correlation function. But so it also could be localized at small times. So in certain sense, strictly it is not Markovian, but it's Markovian up to a constant which we occur at small times. So it is possible to think about as long time Markovianity here. So I think which I have found the long time Mercurianity at this models. It is not Markovian as the inside the correlation time, but it is Markovian outside of it. This is going on. What is going on here, actually? So it is possible to renormalize, or it is possible just to renormalize by this cost of this definition of the Markovianity, and then say that it's a new definition on Mercurianity, which I call long-time Mercurianity. And I said that we need existence of the moments for these results. And it is this condition is actually important because it is possible to consider the correlation function when the first moment of the correlation function does not converge to infinite. And then we have terms of order of lambda, not of lambda squared here, and we have these terms are have power tails in times. So we have exponential Markovian evolution. Oh, maybe I don't define this x, but okay, the x is square root of rho on 1. Okay, maybe I should. I mean this holds here. So I have Markovian dynamics of the density matrix at zero order in usual weak coupling limits type situation. But the first corrections, if this moment is not converged, then have corrections which are totally non-Markovian in sense they not exponential, but they have power tails in time. So that's it. Well, these results could be found in this archive preprints. Well, maybe actually I said all these conclusions. Well, we have obtained the GKSL equations, but in all orders of perturbation theory of Bogolubov-van Hove type. But one should use different initial conditions for these equations. Moreover, sometimes they are not physical. They are not even density matrices. So this is important part of the story. And of course, it is possible. I just showed the non-constructive results, but there are, in this paper, there are explicit formulas for all these generators obtained by some power series. So it is possible to calculate the generator with any given precision, asymptotic precision. So this is it. Thank you for your attention.
Thank you for your talk. Maybe someone have a question, please.
Yes, I have a question. So, in your approach, do you have a prescription how the initial state, or it is chosen?
So it is these are very specific quantities depending on lambda, and they have very specific perturbative series. So it is possible to obtain very specific perturbative series which relates the actual initial condition and the initial conditions for my equation. So there are explicit in this article, there are explicit formula for this renormalization coefficients, so you could calculate it explicitly.
I have a quick question, if you don't mind, Alexander. I'm familiar with the paper of Accardi, Frigerio, and Liu on a quantum central, I think they call it quantum functional central limit theorem, where they developed this. They eventually called it the stochastic limit of quantum field theory. There, when they take the Van Hove limit at the level of the dilation, what they do is they consider a perturbation series expansion where they look at various multi-time correlations. And what they show is ones where the 2-point functions are time consecutive, they call them type 1. These are the ones that contribute to the limit. And the non-time consecutive time correlations, these are type 2. These are the ones which they show vanish identically. But there's no rates of convergence here. I was just wondering, in the proof of your theorem, do you do this type of expansion and break things down into type 1 and type 2?
Well, actually, I have very simple model, and I have I deal actually only with reduced dynamics. So at the level of the both system and heat bath evolution, the situation a bit more complex, and it described, for example, in these articles by Pechin and Balovich. Then the called multiple noises occur. So we have not only delta correlated noises, but noises which are correlated as some derivative of the delta function. So here it is important that I do it only at the level of the system without heat bath. If we speak about heat bath, the situation is a bit more complex. So, and this is and what you're talking about is also so, and actually something is done about it even in this complex situation in this article. But which is important here, I can consider the rotating wave approximation. So some contributions which are contra-rotating vanish at the initially in this model, and these contributions it is similar to the ones that you are saying about this type 2 correlation function. So so it is a bit, your question is interesting in the following way. I think the situation, I have the same situation as in this paper of Accardi and others for this model, but it is very strong question if it is not violated in the case when we have no rotating wave approximation here. So I think then there are possibility of the terms of the second type here. So here it is not the problem, but for me it is of course interesting to generalize it to more physical models without rotating wave approximations. And actually, I don't know if these terms are contribute or not.
Yes, I think with rotating wave approximation, you usually argue there are rapid oscillations and just ignore these terms from Riemann-Lebesgue lemma. That's consistent with the Van Hove scaling. What might be going on here, it might be that all the type 2 vanish identically because of the simplicity of your system. Your system is just a qubit, and basically the system can do only 2 things. If it's down, it goes up, and if it's up, it goes down, sigma plus and sigma minus. And of course, if you apply 2 sigma minuses, you get 0, right? And I think that algebraic identity, the sigma minus squared, sigma plus squared, both equal to 0, means that the type 2 correlations might all vanish identically here. But if you had, say, a 3-level system rather than a 2-level system, so now you've got multiple Bohr frequencies, these type 2 correlations may well be present, and you've got, I think, quite an interesting problem to solve here. So I'm not sure if type 2 actually come into this particular case here, just due to the fact that it's a 2-level system. Maybe we can discuss.
Thank you. Yes, it's interesting problem. Thank you very much. I definitely should consider the 3-level situation and with more complex ones, because I actually have the generalization of this model for multi-level systems, but this is also a bit tricky. That it also allows only one level excitation in the system. So it's a bit the same approximation usually actually done. It's not 2-level, but it's multi-level, but with only one excitonic space. So maybe I also don't see these 2 type correlations there because I omit in the same way as you said. So yeah, it is actually, yes.
But as far as I know, there's no work done on this and no estimate, so that would be a nice problem to look at.
Okay, thank you very much.
Thanks.
Well, if there are no any questions, then thank you for all figures of this section. And now we will lunch so we have a break, and the next session will start at 2 o'clock at UT East +0. So please, at 12 at UT East +0. So please enjoy. Have a lunch and come back to the next sessions.